elliptic curves whose central values do not vanish. So half of these cases are due to codes only, but I will try to not assume anything. So let K be an imaginary quadratic field. With ring of integers, okay. Let's fix an embedding of K into C. And then you can get the Hilbert class field of K by adjoining to K the J invariant of this OK, considered as a complex lattice. So this is a Hilbert class field of K. Let's write H for the class number of K. And let E be an elliptic curve defined, let's say, over E Q adjoin the J invariant of, okay, this has index 2 in H. So this is an elliptic curve with complex multiplication by the ring of integers of K. Let's just write CM for complex multiplication. So what I mean is its endomorphism ring over H is isomorphic to OK. So the classical theory of complex multiplication grew out of a postulate due to Kronecker. And it's based on the analogy between the abelian extension you get by adjoining to H the group of all torsion points on E, and the abelian extension you get by adjoining to Q the group of all roots of unity. So this analogy was actually already observed by Eisenstein. And it tells us a lot of things. For example, it gives you an explicit description of the Galois action on the group of all torsion points on E. And this was used by Doering, for example, to show that the complex L series, the Hasse-Veil L function of E coincides with the Hecke L function, with a Hecke L function. And then this was used to show that it has analytic continuation to the whole complex plane. And then it led to great advance in understanding the Birch-Swinnerton-Dyer conjecture for elliptic curves with complex multiplication. And maybe I'll give you some famous examples. Those are, of course, the ones defined over Q. So the class number is 1. For example, y squared is x cubed minus nx. This has complex multiplication by Q adjoint square root of minus 1, or y squared is equal to x cubed minus n. This has complex multiplication by the ring of integers of Q adjoint square root of minus 3. Let's say n is a non-zero integer. And the family of elliptic curves I'm going to talk about today is no longer defined over Q, but it's really suited for our purpose. So the Birch-Swinnerton-Dyer conjecture, the full conjecture gives you an exact formula for the order of the Tate-Shafarevich group. And because the full conjecture is difficult, it is a good idea to break it up into a p part for every prime number p. And Iwasawa theory has proven to be a very powerful tool in understanding the p part of the conjecture. And for our methods in with Iwasawa's theory to work, it is very important that p is a prime of, or 2 is a prime of good ordinary reduction. So by the theory of complex multiplication, I want 2 to split in the field of complex multiplication. So this imaginary quadratic field K. And it's also useful if the class number is odd. So from now on, let's let Q be a prime number congruent to 7 modulo 8. And let's let K be Q adjoint square root of minus Q. Then indeed 2 splits in this field as frac P times frac P star, let's say. And H is odd by genus theory. Now what each elliptic curve has complex multiplication by the ring of integers of this imaginary quadratic field. So by, again, the theory of complex multiplication, you can get any elliptic curve defined over H whose J invariant is equal to the J invariant of OK. But Gross has introduced amongst all these curves a very nice elliptic curve. This has already actually appeared implicitly in some of the very nice talks we've been having. For example, the talks by Kobayashi and Ota. But I will recall the basic properties. Let's just call it H, A. Such that the J invariant of A is equal to the J invariant of OK. So it has complex multiplication by OK. It's minimal discriminant ideal. It's generated by minus Q cubed, so it's divisible only by 1 prime. And it is no longer defined over Q unless Q is equal to 7, the prime Q. But it's a Q curve in the sense that it's A is conjugate to, A is isogenous over H to all its conjugates by the elements of the automorphism group of H. So even though I'm dropping Q from the notation, please try to remember that A depends on this prime Q. So to state my main theorem, I need to introduce a set of integers. Let this curly R be the set of square free integers such that each prime divisor is congruent to 1 modulo 4 and it's inert in K. The small I, Ri's are distinct prime numbers. So inert in K for I. And given an element in this set, let's write A bracket R to be the quadratic twist of A by the extension you get by adjoining to H the square root of H. So our main theorem is the following. So this is joint work with Yongsheng Li. So let Q be any prime congruent to 7 modulo 8. And let R be this an element in this set. Then the L series for this twisted curve does not vanish at s equals 1. Also, please feel free to stop me at any point if you have questions or comments. So first of all, why are we happy with this theorem? Because by the theorem of Gross-Zagier and Kolyvagin, you can get that the model Veil group of A twisted by R over H and also the Tate-Shaffer-Rich group, they are finite. So the finiteness part is due to Kolyvagin of the Tate-Shaffer-Rich group. And you can try a two-descent to try to show that this is finite, but such an argument doesn't give us anything about the order of the whole Tate-Shaffer-Rich group. So yes.
Why would you expect this to be non-zero?
So priori, of course, I mean, you can actually try numerical computations.
Is there a root number?
There is also, you can
calculation
also
that you
try a
did?
root number argument. Also, you can do a 2 descent to show that this is finite. This has already been shown by several authors. So
second is perhaps a very stupid question: isn't this Kurzweil's or not? Like, what's the I mean, because L value is non-zero and it's CM, so.
So Kurzweil's is when class number is 1.
Okay.
Yes.
Okay. Thanks.
But yes, of course. This came before this. So. Thank you for your comments. And secondly, when Q is congruent to 7 modulo 16, this theorem is due to Coates and Lee. So the new case we are contributing is Q is congruent to, so this is half of the primes congruent to 7 modulo 8, and we are contributing the case to the case Q congruent to 15 or minus 1 modulo 16. And why should this case be any different? But they use Iwasawa theory at the prime 2, and then like a small difference in congruence class modulo powers of 2 can have deep consequences. So maybe this is a good time to fix a prime, one of the 2 primes, or lying above 2 in K. Let's pick this frac P. And then you can, you choose the sign of square root of minus Q so that the normalized p-adic valuation of minus square root of minus Q minus 1 divided 2 is greater than 0. Okay, and what's another interesting thing is that instead of Iwasawa theory for this elliptic curve A, we need to use Iwasawa theory of the elliptic curve of the abelian variety you get by restriction of scalars from H to K. So let B be the abelian variety you get by restriction of scalars. Then B over K has dimension H. It's an abelian variety. Let T be the endomorphism ring of B tensored with Q. This is a CM field of dimension of degree H over K. let's let F be the field you get by adjoining to, oh, okay, no. So we need to pick a prime in T lying above this frac P, and Coates and Lee showed that there is a particularly or special prime, and they do Iwasawa theory at this prime. So the following prime exists, and its existence was shown by Coates and Lee. Let's call it curly or frac capital P. So this is an unramified degree 1 prime of T lying above frac P. And let's let F be the field you get by adjoining to K the frac capital P square torsion points of B. And then you can show that B has good reduction everywhere over this field F. And let's let F infinity be the field you get by adjoining to K the O frac capital P power torsion points of B to K. Then you can check that the Galois group of F infinity over F is equal to delta cross gamma, where delta is cyclic over order 2 and gamma is isomorphic to Z2. Sorry. So there is a unique prime satisfying this property after fixing this frac P. Oh, sorry. Yeah. Thank you.
So in particular, this T is different than H, even though they have the same degree.
Exactly. Actually, we have T intersection H is equal to K. Thank you. Then let F infinity be the maximal abelian 2 extension of F infinity and ramified outside of the primes above frac P. So maximal. Yes. Then you let X as infinity be the Galois group of F infinity over F infinity. Then The following was shown by Coates and Lee.
Yuka? Sorry, there's a question in the chat. The question is from Jianing Lee, and they're asking if the Galois group should be the Galois group of F infinity over F or F infinity over K.
Ah, thank you. So, okay, they show that this xf infinity is for any q congruent to 7 modulo 8. This is a finitely generated Z2 module of dimension given by the following of like Z2 rank. And 2 to the L minus 2 minus 1, where L is the frac P adic order of square root of minus Q minus 1. And some remark. We have L is equal to 2. So in particular, f infinity is equal to 0 when Q is congruent to 7 modulo 16. But when Q is congruent to 15 modulo 16, we have L is greater than or equal to 3. And in fact, by the work of Jianing Li, you can show that xf infinity is not equal to 0. So we need to understand the corresponding Selma groups very well.
Just to make sure I understand, I think you can rewrite the definition of L referring only to integers by saying it's the order at 2 of Q plus 1, all minus 1.
Sorry, can you say that again?
L is also equal to the order at 2 of the integer Q plus 1 minus 1. Because you can take this number and multiply it by its conjugate, which is going to be almost co-prime to P. It'll just have a single factor of P, and then take the order at 2. That way that you can compute this explicitly. This is where the 7 mod 16 comes from, because that's where the 2-adic valuation of Q plus 1 is exactly 3.
So here I fixed the cube root, the sign of the cube root of square root of minus Q so that this holds.
Yeah. I can talk to you about it later.
Okay.
I had another question. Do we know that x of f infinity has no torsion? I just asked because you jumped directly from having rank 0 to being equal to 0. So I was just curious.
So yes, the answer is yes.
Okay.
Is it this kind of results which say that there is no pseudo-null submodule?
Yes,
X? Yeah.
exactly. And yeah, you use Nakayama's lemma. Okay, so we need to show the following key proposition. So we have the frac capital P Selma group of B over K is isomorphic to Z mod 2Z. So that in particular, I mean, we know that B has torsion of order 2 torsion over K. So the model vector group of B over K should be finite. And this tells us that the frac capital P part of the Tesha-Hurwitz group of B over K is finite. So its frac capital P primary part should also be finite. And this was used to show that, oh, okay, maybe I should say something about the proof. Gross has shown he has done a 2 descent argument to show that the 2 Selma group of A over H, the G invariant part, is isomorphic to OK modulo 2 OK. And then we use the fact that G is the Galois group of H over K. So its order is equal to class number H, and we assume that it is odd. So using that, you can write it as frac P Selma group times frac P star Selma group. And we also know that the model veil group of B over K coincides with the model veil group of A over H, and the frac P torsion point on A is isomorphic to the frac capital P torsion point of B as modules over the Galois group K bar over H. And then you can show that this restriction map is an isomorphism. So that's the idea. And using this, we show the following. The Selma group, the frac capital P infinity Selma group of P over K, the gamma invariant part is finite. And this Selma group without the gamma is dual to the Iwasawa module X F infinity. So we didn't have X F infinity is equal to 0, but we could show that the corresponding Selma group has its gamma invariant part is finite. And that's enough to use the Euler characteristic formula to say, to show non-vanishing of a characteristic ideal for this Iwasawa module XF infinity. And okay, now let's introduce some more notation. So let's write psi for the Hecke character of H, A over H. And let's write phi for the Hecke character of B over K. Then you can show that psi is equal to phi composed with the norm map from H to K. And so using the Euler characteristic formula, you can relate the order of this Selma group to the non-vanishing of this characteristic ideal, and then use a main conjecture in the case, well, basically it's due to Coates and Lee, adapted to our case, to relate it to a p-adic L function, which interpolates the L value we are interested in, and we can get the following. So we have this Hecke L value divided by a complex period coming from the elliptic curve A over H. It's Néron differential. This lives in the field, the compositum HT. And for any prime lying above this frac capital P, let's call it curly P. We have that the curly p-adic valuation of this. Sorry, this is of HT. This is equal to -1. And in particular, recall that the complex L series of A over H coincides with the complex L series over P over K, which can be written as a product of, oh, I forgot maybe. So, okay, here I fixed an embedding of, let's say, I of T into C, extending our embedding of K into C. And there are H distinct choices, and by varying them and taking the product, you get the complex L series of B over K. And so in particular, relating it back to our original elliptic curve, we have that the base curve has central value not vanishing at s equals 1. But to get the non-vanishing of the twist, we really need this precise p-adic valuation. So now we need to...
Excuse me, what was omega infinity?
This is a complex period coming from the Néron differential of A over H.
Over H.
Yes.
Okay. Thank you.
Yeah, we have an explicit, I didn't write it down, but we have an explicit equation for.
Sorry about the rationality. This L pi bar 1 divided by the period is in HT, but isn't the initial elliptic curve defined over H?
Yes, but this is Hecke character of B over K, and sorry,
I mean, probably it is correct, but I'm just wondering why one needs a composite term H and T.
So in the end, in the end, it's not going to really matter, but it's just maybe let's just keep it like this because it's safer. Because I'm going to now but I think it had to do with the fact that the choice of this period. Yeah, it's coming from A over H rather than. Yeah.
Excuse me. So I was just to make sure. So H has not necessarily class number 1.
No. It's only
so,
class number. Its class number is 1 only when Q is equal to 7.
okay. So Néron. So we have to take Néron model, but is it easy to normalize somehow because OH is not necessarily PID? So
Gross has shown that there is a like globally minimal model for this elliptic curve.
Anyway, we can normalize. Maybe I screwed it up. Thank you.
Let's let the given R in curly R, let's let phi R be the Hecke character of the twisted abelian variety. PR. So that phi r is just equal to phi chi r, where this is the quadratic abelian character defining the quadratic extension h square root of r over h. Sorry, k square root of r over h. Now we want to show we will do an extension of so-called Zhao's method. He used this initially to study the two-adic valuation of algebraic part of the central L values of quadratic twists of the congruent number curve. So these were defined over Q, and we will adopt it to our abelian variety B. But the key ideas are the same. So first is averaging of L values as D runs over divisors of R. And induction on the number of prime divisors of R. So, okay. We define the imprimitive Hecke L function L R psi so for the dividing R, over no. Let's just keep it like this. By summing over psi d. So B runs over integral ideals co-prime of K co-prime to R and the prime of K lying above Q, and the norm of B to the power S. And by the work of Doering, the Dirichlet series on the right-hand side converges, has analytic continuation to the whole complex plane. And we show that this square root of R this is in the compositum HT, and for actually just to make it easier, let's define HR to be the field you get by adjoining to H square roots of these distinct prime. We have this is in here, it's actually in HT, but I want to introduce a prime. And for any prime, let's say curly D of HRT lying above this special prime, we have the curly D-adic valuation of this is equal to the number of distinct prime divisors minus 1. And in particular, by the same argument, the twisted curve L value does not vanish, which is what we said in the main theorem, because this Hecke L value doesn't vanish. So how do we do this? We introduce the following averaged L value, big pi R. It runs over all divisors of R. So these usually imprimitive Hecke L values. And then there is a classical result relating this to Eisenstein series of weight 1. And summing over this, you can write it as a trace of Eisenstein series, and using this, you can show that this is equal to 2 to the k times t, where t is something with integral valuation. But this is also equal to for ease of notation, let's write LD to be square root of D like this. So what we want is the valuation of LR. And this is equal to LR divided by square root of R plus middle sum, where D is a divisor of R, but D is not equal to 1 or R. And you can take out the Euler factors so that the remaining term is primitive. The norm of Ri is Ri squared. Plus the last term, which is L1 divided by, times all the Euler factors. So from I1 up to R of this. And you can believe me that each Euler factor contributes +1 to the valuation. And we have shown that this has a valuation at least okay. And we showed in this theorem, which dealt with the base curve, that this has valuation -1, and sorry, this is k. So this has valuation k. And so this is the base case of the induction, let's say. So here we have valuation by the induction hypothesis. This has k, the number of distinct prime divisors of D -1. And from the Euler factors, you get, so these are like Ri dividing R divided by D. So plus k minus kd. So this is k -1, but you're summing over it. So we can just say that this is at least k -1. And unfortunately, it's not enough to conclude that this has periodic valuation k -1. So we need to, in addition, use the fact that, just one more minute. If you divide this LD by L1, you get an element of T. This has residue field degree equal to 1. using this, you can divide everything by L1. And you can write this term like explicitly, and like you sum it over the prime divisors, and you can show that so you're dividing by something with valuation -1. So in the end, you get, so this has valuation k+1, this has valuation k, and you can show that this has valuation k+1, and from this you can conclude that the valuation of this LR we are interested in has valuation exactly equal to k, and therefore it doesn't vanish. I think my time is up, so thank you very much for your attention.
Questions for the speaker?
Sorry, I'm just trying to understand. The theorem you mentioned on this board is a consequence of some main conjecture proving some.
Yes, it's a main conjecture for, it's a combination of a main conjecture of A over H and B over K. For B over K, we use this special prime frac capital P.
But then can the same argument be applied directly for this quadratic twist?
That's excellent question. So it was actually, I don't know, maybe easier to do it this way, but exactly. Yes. Thank you.
There is one question in the. Please recall what is a Hecke character?
So you can think of it as like it's on the ideals of H, and it looks like so if you get an ideal A in OK, you get an element alpha, and I think so. Well, I think alpha to the anyway, and I think alpha is a square modulo the prime above Q or something, but it describes this action, the Galois action on this torsion points of A, and that, yeah, from the theory of complex multiplication. Maybe there's an H.